Good morning, everybody. This is a wonderful occasion and a difficult one because Professor Noordain has informed me that there are 250 of the young people in the audience here. So my talk may appear a bit trivial for the experts. So I would like all the experts, including those who have the Nobel Prizes, to go to sleep in the coming hour and to let me just talk to the young people. So I want to start by this amazing eye for you. Many of you might know this already, but I will just try to review it. That in our eyes, there is a fluid that has a refractive index of about 1.3. And the refractive index of air is about 1. And together with the lens inside our eye, if a light is coming, and that's how we see, if a light is coming into this eye here, we focus this light because the refractive index here is higher than outside, and we have a beautiful, flexible lens that it will take you years and years, if not ages, to manufacture it properly. And then you will focus the image on what's called the retina. And when you focus this image on the retina, there are cells in our retina here that responds. It's called photocells, and send a signal into our brain. And that's how we see. The remarkable thing is that two things that I want you to take with you from this. One, since Professor Noordain spoke about molecular frontiers, the molecule inside the cell here called the rhodopsin, it responds to the light by twisting around one single bond in about 200 femtosecond. A femtosecond is a millionth of a billionth of a second. However, the reason we see the image with clarity there is because, as I said, of the fluid and the lens. So the light that's coming parallel to your eye now focus here at a given spot on the retina, and this is transferred into the brain. So we see, and we see in 3 dimensions. And I just thought that to show you how we see a cat like this, and what do we really mean by 4 dimensions. You see the cat as a whole, defined in space and in time. It moved from this point into that point. But physics tell us that the equivalent picture of this is to allow every point on this cat to define as 3 fundamental points in space called X, Y, and Z. And there is another variable called time. And these are the 4 dimensions that I want to talk about. How can we take objects that you even do not see with your eye and take them into the domain of 4 dimensions, into the X, Y, Z, and time? And I only know of one method to do that so far. So you saw the other one with your eye, but this one you can't see with your eye. And this was a problem in 1832 by Mr. Marie, who developed a technique. If you hold the cat upside down, and I don't want you to do that, and you let it go, there's some knowledge here, and people at that time thought there is a vital force that allowed this cat to land on a pillow with all 4 feet in the right position. We haven't seen anything in between here of this because your eye cannot see neither in space nor in time what's happening as this cat goes from here to there. But this problem was solved And was solved actually with some music. You might hear a little bit of music there. So you can see all the snapshots here has been, lower a little bit please. And you can see this is a very famous scientist. You might find his name in your chemistry and physics books, J. Willard Gibbs. In 1894, he even gave a talk about this at Yale in the mathematical club because it wasn't clear why the cat does this. It turns out it has something to do with angular momentum and the ability of the cat to twist around during the motion. Now, if we want to go from a cat with a dimension of centimeters to photograph and speed of about 1 meter or 2 meters per second, your camera of about 5/1,000 of a second is capable of actually taking a snapshot of this cat in action. And now we know how to do it. However, if you go to the molecular science, again, as Professor Noordain pointed out, in the molecular science, the problem is much more difficult. The distance you're talking about here is reaching, you see how many zeros? 3, 6, 9, 10, 11. So it's a very small distance. We call it angstrom or nanometer. And the speed that the atoms move here is about 1 kilometer per second. And so you find that the spatial resolution in space, in order to see this, you need a nanometer resolution. Nanometer is a billionth of a meter, and the femtosecond in the time domain. So in time, that was solved, even for the Nobel Committee in 1999, because here we knew that this is 1 kilometer per second, and the distance is about an angstrom. So right away you realize that in order to see this in time, you need the time resolution of femtosecond. But what about the many, in fact, this took about 9 Nobel Prizes here, from the first one that was given to Van Hove of Holland, and it built up until we reached here the femtosecond. And similarly, for the structure of these molecules, you heard of the Watson and Crick, and also there has been work using the electron microscopy, beautiful work, and many people. I think one of the latest, for example, is Roger Kornberg's work on RNA polymerase. It's a whole machine here, a whole molecular machine that we now know how it functions, at least the structure of it, but we don't know how it functions exactly. So the time resolution problem has been solved. And we knew how to do this with lasers and other tools. The spatial resolution in 3 dimensions has reached the ultimate. From the table salt all the way to molecular machines like the one I mentioned to you. What we don't know how to do, and that's what my group and I focused on in the last 10, 15 years, is how do you get the space-time resolution, the joint space-time resolution. Just like the cat moving in front of your eye in space and time, we also wanted to see this joint resolution, and that is the 3 dimensions in space and 1 dimension in time. Now, we don't know too many, or at least I don't know too many other than microscopy, and that's what I would like to spend some time on. You heard already in the first part of the workshop, I showed you the eye, and the eye can resolve up to a human hair. And the reason for that, without getting into the details, there's something called the diffraction limit of the eye. So the eye has an aperture, and an aperture diffracts the light, and you can't do any better. And you heard from 2 speakers in this symposium that they can go beyond this limit and let us say into tens of nanometer with light microscope. With the electron microscope, you can actually go to the size of the atom. And this was shown beautifully in static experiments long time ago. You can actually have a direct image of the atom in space. And the first microscope was developed by Mr. Knoll and Roska in the 1930s, and they had to wait 50 years because the Nobel Foundation here is very careful. So the Roska received the Nobel Prize jointly with Benning and Rohrer. And you can see for fundamental work in electron optics and for the design of the first electron microscope. However, since the 1930s, in electron microscopy, only static slow imaging was possible. You could not see the joint resolution that I spoke about, meaning that the time resolution and the nanoscale jointly was impossible. So we had to bring in the fourth dimension. And this is our work since 2001 at Caltech. But I want to share with you, and that's the key, it would be impossible to work if we do not understand this, and you will understand it because it's a simple concept called the single electron concept. And the same when you see me right now. It's called the single photon vision. So looking at me, you're collecting some photons, but you're collecting these photons very rapidly, that your eye, in a fraction of a second, can integrate this. So what you will see here are some dots coming from this behavior on the retina that I mentioned about, and that appear to be the evolution of some image. We don't know what it is. But if you waited another millisecond or a thousandth of a second, it seems to be something is coming here, building up in the image. And if you wait more, you're going to see a more clear picture, and now this is the picture. So what the take-home lesson is that you can build a photo, but you can build it from single photons building up and integrate in your eye until you see the complete picture. We did the same thing with the electrons. The electrons, unlike photons, have charges. And because they are charged, they repel each other. And when they repel each other, we lose all of the time and spatial resolution that I talked to you about. So we use the idea of the single electron imaging to, unlike all electron microscope that we know about, where the electron comes at once here into the object and image the object at an integrated time, in our design, the electron comes as a single trajectory and hits. And then because we do it with precision, we repeat the experiment again and hits, repeat the experiment again and hits, and that's not any different from this photon image that your retina is developing over time. So if you waited a millisecond or a second in our single electron microscope, you will see the image identical to this, but now we have the shortest time resolution possible. It's actually 11 orders of magnitude have been improved compared to other all microscopy that we know about. And as such, we can now control the electrons that are coming out. They are not random anymore. They are not punched or anti-punched, as the physicist will say. And one of the first experiments we showed, maybe here, is to show here that if we take a piece of graphite, nanometer, and we can show the carbon planes here with a resolution of about 3 angstrom, or we can see a molecular here distances of about 1.4 or 1.5 nanometer, but the time resolution now is the shortest ever achieved, and this is joint. This is both time and space. And one of my former postdoc have just about to publish a paper which now he can reach, actually with this resolution, about 2 femtosecond in terms of a tip here. And another postdoc is now reaching 82 attosecond. Attosecond is 10 to the minus 18. So you're seeing that even in a microscopy, and the electron repelling each other, but by this concept here, we are able to reach extremely short times to look at the dynamics of these systems. So this is how it works now. Here is a microscope, and now we use lasers to create the electrons. Before, as Professor Nordin mentioned, all our work was lasers. Now what we do, we use the lasers to create electrons in the microscope, but after the electrons are created and the sample is activated by another heat pulse, they meet, we take an image, and then we can see, for example, a nanotube, just 1 nanometer in width. We can see the temporal behavior of this evolving at 0 time and at, say, 600 femtoseconds. So we have the joint resolution of space and time. We can scan it, but I will not bother use this. And this is in one of our microscopes at Caltech, and you can see all of these fancy laser beams here, but we have to go here and do the experiment using this idea of the single electron. There are some paradoxes there, and maybe I will leave them until we get to the questions period, but there is an issue about the uncertainty principle, which I spoke about or wrote about some time ago, because the pulse is extremely short of the electron that's imaging. Would that interfere with the measurement? These are all interesting questions, but if you are interested, you can read about them in this book that was published with Professor Thomas in 2009. So the beauty of microscopy, and I don't know of too many tools that can do that. One is that you can obtain a real space image. The image in front of you of the microscopic system, you can see it magnified 1,000,000 times or more. You can also look at the inverse space, namely the electron diffraction. You can also look at the energy space of the electron. As the electron interacts with matter, it loses some energy or gains some energy, and in that energy space spectroscopy, you can get quite a bit of information that you don't get by other techniques. And there is a huge number of variant techniques with microscopy, with electron microscopy. Tomography, holography, as you will see, many, many other things that you can do. So this slide here is a show-off slide because I like to show you that we have been active in publishing since we started to build this in 2001, and many of the papers have already been published. As a matter of fact, I might show you a movie of the latest about how do we see in space and time the charge moving from a P into N, and how do we map this out in real time and space. So I'll just give you a few examples of the techniques. Electrons can be focused to the size of the atom. There are now electron lenses that you can focus the electron beam down to the size of the atom. I don't know of any other method that can do that. And we have done this, and when you focus it like this, you can learn about a specific particle that's undergoing the chemistry or the physics transformation. Electrons also, now we have done 4D tomography, And we can tilt the sample on the microscope in different directions. And by tilting the sample, now you introduce the element of time and angle here into every frame. And as such, we can also obtain what's called tomography, the actual three-dimensional space and the change with time. And an example of this is a ring made of nano carbon tubes, and it would be impossible to know what are the frequencies involved in the motion. But with tomography, you can tell at the end here the displacement is different from here, for example. So you can actually get the normal modes of a ring like this at different places in space and in time. This is a nano arm that shows you how we can do this for a particular nano device that was made at Caltech. And you can see the arm now is moving in 3 dimensions and how this motion is affected in time. And in fact, in this paper in Nanoliter, we analyze the normal mode at this point, and at that point. So it's no longer one point that you're trying to get the temporal behavior of it. It's the space-time behavior that we are after. And as you can see, we can create this normal mode. And there is an interesting issue here about, is the motion periodic or quasi-chaotic? All of this are interesting issues to address. This, and especially for the young people, we discovered by accident or serendipity. And probably it's one of the most powerful technique that we developed. It's called near-field electron microscopy. It turns out that the electron does not interact with the photon that we have. And this is clear because you do not match neither the momentum nor the energy in space. However, if you put a nanostructure, that releases restriction on the so-called uncertainty principle. And because of this, the electron and the photon interact. And when they interact, they give you an image of the electric field around this object here. And you will see this in a minute. And we didn't realize this in the beginning until by accident we observed something that is unexpected. So you need the electron, you need the photon, and you need the nanostructure. And what we did, we twisted the idea that we're going to use the electron and photon to learn about the nano structure. And here it is. If an electron passing through material, you expect the electron to lose energy into the material. And losing energy to the material will be such behavior here, meaning that this is the initial electron in time, and you can lose a photon or 2 or 3 or 4. But what we did not expect at all is that we gain photon and 2 and 3 and 4 and 5. It's a highly quantized 1 photon, 2 photon, and actually we observed up to 40 photons here as a result of the interaction between the light, the photon, and the nanostructure. So if you plot this in electron energy, you see right away that we are seeing these photons being gained by the electron. The electron is being accelerated by the light because of the nano structures. And so here is a movie that you see that we can take now a snapshot, and we are seeing the field around the nanotube being built up and decayed as a function of time. And this is the so-called near field. So now we can actually study plasmonics, photonics. All of these terms that you hear about is immediate nanometer behavior of this nano tube. You can do also beautiful polarization experiments, which we did parallel to the tube and perpendicular to the tube. And even in protein vesicle, you can also see the effect Here is a vesicle, and that's the theoretical calculation. And this is a vesicle that is tilted about 30 degrees to the plane of the microscope. So, few applications. This was one of the first we did in '08, is that if you take a carbon sheets of graphite, and it's about 10 nanometer or so, and you activate this with an infrared pulse, you can actually create these oscillations that you're seeing right now. And these oscillations here is the sound waves going from one end of the nanostructure to the other end of the nanostructure, going back and forth. If you take the speed and the time period, you can learn something very important called Young's modulus. So you're getting the elasticity of the material, the elasticity of the material as you change actually the dimensions of these nano materials. This is an effect that we saw that was remarkable and was against our intuition in the beginning, but we can also see the drumming of the whole. These are about 10 nanometer, 10 nanometer. And we can see the drumming of this plate in the microscope going up and down. And in fact, the next one, also we can get the Young's modulus. You can see it here, if the sound will be good. So in the beginning, it's chaotic. But as we go on with time, you will see it's almost like a heartbeat. You're seeing the drumming of the entire carbon sheet. The carbon sheet is about 10 nanometer in thickness. And this is a real image in the microscope. This is the latest, and you will hear about something exciting, which is the single graphene layer. And we're seeing an effect there that will be very, very surprising because this is acting like a laser cavity. We can actually see the radiation is going back and forth between the two ends, forming beautiful waves, and we can understand this, and you will see it soon, in terms actually in these materials now, the light, the phase velocity exceeds that of the speed of light by a factor of 2 or 3. This is what we call nano instruments. And these are interesting to us because you can manufacture nano harp. In this case, the length of the arm is varying, but roughly the thickness is the same. And you can hear this is for the nano harp in space and time. And if you go to this one, this is the piano. The thickness of the key is varying. And so you can hear a different frequencies. And we know this by taking the so-called Fourier transform to know what frequencies do we have. And because we know this, we can actually control one key. And if we can do that, it's like the fork. So we can supply the structure with a given frequency multiple such that we can see only one key that is acting as a fork. There are other applications, but I don't want to. This is the one that I mentioned to you about. I believe this is the first time ever that you can see the flow of charges in a semiconductor material, the P and N junction. And at the junction, you can see the build-up of the charges on one side and the depletion on the other side. And this was just published very recently. And here is a movie showing this. The depth of the surface layer here is a fraction of a nanometer. I think that I did something wrong here. And what I want to do is this one here. So now the charges are depleting at the junction, and the white and black is telling you that there are more electrons in the white, less electron in the black, and you can follow this as a function of time and at any point in space as displays. Finally, some of the stuff that we have been playing with in the biological world, we take a DNA network, and actually we use the electron beam to cut one of these networks here. So we create now an assembly that looks like this, for example. And just like you shaking the Empire State Building and getting an information about the elasticity of it, you can do the same experiment here by shaking this structure and getting the elasticity of the DNA. So here we can find out how fast are the frequencies and the normal modes that are involved in here, and then we can tell you how rigid this is from the motion in space. And you will see why this is important when we come to cryoimaging, which I know you will be hearing about and heard about. But here is the case where elasticity is extremely important. And that's the amyloids. This is a lot of work in Cambridge, pioneered by Chris Dobson and his group. And in fact, the person who did the work at Caltech, Fitzpatrick, is a graduate student of Chris. And here we can take an image of the amyloid itself, and we can also get the diffraction. And what's important is that we can actually see the response in nanometer of the amyloid in the chain and across the chain. So we'll learn something about the nature of the bonding. But as importantly, we can do this experiment by shaking the amyloid and finding out about the resonance that you're observing here. And this resonance right away gives us how stiff the amyloid. And it turns out to be gigapascal. So you don't want this amyloid to be building up in your brain because it's too stiff. Actually, our membrane cells have elasticity of megapascal. So it's stiffer by about 3 orders of magnitude than the membrane elasticity. And this have serious consequences that if you want to know more, there is a recent paper in Physics Today about the biological importance of this. I'm showing you this here because we can do tomography again on the amyloid. And this is how amyloid rods look like in space. So I want to conclude by telling you that it's remarkable of how all of us build on the work of others. Here was 1897 when the electron was discovered by J.J. Thomson. And here is a famous paper by de Broglie in 1924, which I think was so fundamental that Einstein himself was so excited about this paper, which tell us that materials have both the particle and the wave characteristics. Electron microscopy, as I mentioned earlier, was Nolan Ruska in 1933. Aaron Klug and company give us the third dimension because he allowed from the image and the diffraction that you can go back and get the structure in 3D. And the work in Cambridge since then by Henderson and many others has been at the forefront of development. This is the scanning tunneling microscopy. These are all microscopy. Here is diffraction that I will not talk about. And finally, we like to feel that we added the fourth dimension because we can get now all of this in time. And as I said, the beauty of this electron microscope is that you can get all these attributes here, including the cryo that I mentioned and showed to you, and many of the other techniques that are very well known. And if you are interested, this is a book that I wrote with Professor Thomas, and you will find many of these things. And I'm glad to mention that the microscope itself has now been commercialized not by me, but by a company called FEI, which is very famous for electron microscope. Now, Professor Bengt Nordheim is standing up. That means in our business that I should finish. But what I'm going to tell him that I'm not going to finish. And let's see what he's going to do. I mean, let's find out. So here we go. The future is fantastic because I just want to mention a paper in Science, not from our lab, but from Cambridge, on getting the ribosome channel especially, by Ramakrishnan and his group. Fantastic piece of work at a resolution of 3.4 angstrom, and without having a crystal. One of the great problems in X-ray crystallography is to have a crystal. Here, we are talking about single particles. And of course, not to mention, you can do clusters and you can do atoms. All of this is true. And I'm going to skip all of that, Dr. But I want to talk to the young people about one thing that's very important to me. And essentially in all my talks, I show these 2 slides. One, not anything we have done so far with my group is all planned and all drawn in a piece of paper from A to Z. It is not true. It doesn't work that way. We simply are curious. We are curious about what is going on, how do we measure this, why, and what is the mechanism, and so on. So this is like Alice's Adventures in Wonderland, and I have written about this. Unfortunately, in some places of the world, curiosity now is becoming not the word of the day, and more that we have to produce things and so on. But it is very important for the young people here to remember, we're doing this for fun and to try to understand phenomena of nature. Thank you, Professor.
Thank you, Ahmed. Fantastic talk. There is some chemistry here. You know, Alice, in order to go through the door, she had to take the bottle on which it said, "Drink me." Yes. So while George is rigging his things, we have time for one question. Here we have a hand.
Thanks for... It's working?
It's on.
Okay. Thanks for this very nice presentation.
I'm sorry, can you be louder a little bit? I can't hear you.
Okay, thanks for this very nice presentation. I just have one interesting question. Since I'm interested in the cancer research, and this is what I'm doing in my PhD, so can we get an application from the resonance and from the imaging of measuring plasticity of DNA as a diagnostic tool? And you know, in the cancer, we are integrating so many mutations to the DNA. So does these structural or point mutations, or very minute changes in the structure, can lead to a sort of changing in the plasticity, and so that we can use it as a diagnostic tool for the prediction or for a precise diagnosis of cancer?
Boy, that's a big one. Diagnosing of cancer. Nowadays, if you have something good idea like this, you start a company and you become a millionaire, It's a big question. Well, I think 2 things or perhaps one thing I should emphasize. In all of this work, we try, the dosage that we are feeding is so small that we are not perturbing the system. So for example, when we excite the DNA or the protein, it's a heat that's being transferred with a very low dosage, so it allows us to see the images and diffraction with the electron. At very high intensity, if we were to do these and change the properties, you also get into other problems, which I'm not aware of yet. So I can't really answer the second part of your question.
But I think he has a good idea. What you have in DNA when you have something which is wrong could be mismatch. And a mismatch is associated with a loss in rigidity. So what you look for is the dynamic plasticity. And of course...
Oh, I see, as a function of the, for example, the mismatch that exists.
Yeah, exactly.
Oh, yes.
Is it a mismatch or whatever sort of mutation that we are getting? Because also we have an associated proteins with the DNA, and even you can get a change in the protein itself rather than the mutation in the DNA. So as
don't speak more, because you should patent this and not speak about it.
Okay. So can I just tell something finally? Because actually it's a personal request, since I'm coming from the same city you're coming from originally, from Egypt. So I'm just glad to have a picture with you afterwards, after we're done. It's a personal request.
And he's making it public so it can count. Okay,
yeah, exactly.
We'll do that. Yes. We'll do that.
I'm sure you have many good questions, all of you, and I direct myself to youth here. There will be a possibility that Magdalena will announce how you could transfer your messages as questions to the speakers. So if you put it down on a piece of paper, we will collect it somehow. Thank you once more.
Thank you.